Hi, join me as I dive into the challenge of uncovering what makes our sun so amazing and discuss some mind blowing facts along the way. The sun is the vital star at the center of our solar system, and it is very easy to see why. Without it, we would be a frozen, dark, and lifeless planet. The sun's importance goes way beyond just providing us with light and warmth. It is the very reason that life exists in the first place. So, without further ado, let's begin. One thing is for sure, the sun is often misunderstood. Many people think that the sun is just a big ball of fire, but it is actually a massive celestial body with a diameter of about 1.4 million kilometers. That is 109 times bigger than the Earth. Another common misconception is that the sun is just a few thousand kilometers away from us. But in reality, it is about 150 million kilometers away, which is a huge distance. A lot of people also believe that the sun is responsible for most of the extreme weather patterns on Earth, like hurricanes and droughts. But the truth is that the sun's energy is what drives the Earth's weather patterns, but it is not the sole cause of these extreme events. We also have to consider the Earth's own internal processes like volcanic eruptions and ocean currents, which play a huge role in shaping our climate. The sun is indeed a big ball of hot glowing gas, but it is so much more complex than that. The sun is actually made up of different layers, including the core, the radiative zone, and the convective zone, each with its own unique characteristics and functions. Radiation is being emitted and absorbed in all the layers of the sun, but we only see radiation from the surface. Most of the radiation from below is absorbed before it reaches the surface. To understand what we are seeing when we look at the sun, we need to understand the interaction between radiation and matter. For instance, most of what we know about the solar atmosphere comes from studying its spectral lines as well as the continuum. This study of radiation's interaction with matter is known as the radiation transport theory. Broadly speaking, energy transport can happen in three ways: radiation, convection, and conduction. In radiation, photons carry the energy, while in convection, energy transfer by mass motion of a fluid takes place. I'm sure you have seen the tea leaves or grains of rice going up and down in water when they are boiled. As the water is heated from below in a pan, the rice or tea leaves gain energy and come to the surface, transfer their energy to the cooler material on top, and sink back down. It looks like they are going in a circular motion vertically in the pan. This is what happens in convection. In conduction, two surfaces which are in direct contact with each other experience transfer of heat from the hotter to the colder surface. It is indeed fascinating to realize that these same laws of physics which explain processes around us are also active in different regions of stars. The structure of the sun is truly mind-boggling. The core is the sun's central engine where nuclear fusion reactions take place, releasing an enormous amount of energy in the process. This energy makes the sun shine brightly and is responsible for life on Earth. The radiative zone is the layer just outside the core where energy is transferred through electromagnetic radiation. Most of the visible photons we receive from the sun originate in its photosphere. As we discussed in the episode on spectra, atoms absorb and emit at particular wavelengths corresponding to the spectral lines. So you may ask, if sun is abundant in hydrogen, why does the spectrum shows continuum at all? Now that is because despite its abundance, the neutral hydrogen cannot contribute to the continuum. The continuum in the sun primarily comes from the hydride ion in the photosphere. A hydride ion is a hydrogen atom to which an extra electron has been added. Now this extra electron obviously is held very weakly to the atom, so very little energy is required to remove it again. The hydride ions are present in the photosphere because there is a lot of hydrogen and a large number of free electrons to collide with those atoms. If we have a hydride ion and a photon strikes it, the photon is absorbed and the electron is set free. The hydride ion is a bound system. The final state has a hydrogen atom and a free electron, and hence this process is called a bound-free process. The energy of the incoming photon is not restricted in this process because as long as the photon has more energy than that is required to remove the electron, the remaining energy can be transferred to the electron as kinetic energy. Also, a continuous range of photon energies is possible. The bound-free process therefore contributes most to the continuum absorption. The continuum emission from the sun is the result of the inverse of this process. The nuclear fusion happening in the core of the sun is responsible for its energy, as we discussed in great detail in the video on the energy sources of stars. Do check it out. In short, when 4 hydrogen atoms combine to form one helium atom, 0.7% of their total mass is lost as energy. This mass loss appears as the solar energy radiated by the sun. As shown in the simple calculations here, around 600 million tons of hydrogen fuses into 596 million tons of helium every second in the core of the sun. But fusion reactions are not possible in the entire sun because the temperature required for nuclear fusion to take place is available only at the center. Remember that the temperature in the sun changes as a function of its radius. The core at the center is the hottest part in a star. Models in agreement with data suggest that about 10% of the mass in the core of the sun is hot enough to sustain nuclear fusion. In stars like our sun, the density and pressure in the central core is large enough that hydrogen can fuse into helium via the proton-proton or pp chain reactions. The slowest step in this series is the first step, which requires a proton to decay into a neutron. This kind of decay involves the weak force, one of the 4 fundamental forces in nature. The rate of energy production in the pp chain reaction depends on the 4th power of temperature. The pp chain reaction is responsible for converting hydrogen to helium and production of energy in the sun and even some stars less massive than the sun. The best thing about observing the sun is that we do not have to worry about the light gathering power of our telescope because there are plenty of photons coming our way. So our sun is the one star that we can study in great detail. This is also the one star for which we can try to spread the image over a larger area and make it easier to see the detailed structure of the surface. So what we want is a telescope with a long focal length to give us a large image scale, something like this solar telescope on the Kitt Peak mountain. When we study the sun's surface on a scale of a few arc seconds, we see that the sun does not have a smooth appearance. We observe a structure which is called granulation. This is a pattern of lighter areas surrounded by darker boundaries. The dark areas are actually not dark but cooler than the light areas and therefore appear darker relative to them. These granules have a typical size of about 1,000 kilometers across. The granulation pattern keeps changing with time, with the new pattern appearing every few minutes. This granulation can be explained by circulating cells of materials called convection zone. Remember our example of tea leaves boiling in water? The gas in the brighter, warmer regions is rising up from below, and the dark regions or the cooler gas is falling back down. In addition to granulation, there is another variation called the 5-minute oscillation, in which parts of the photosphere are moving up and down. Astronomers now think that this convection results from sound waves in the upper layer of the convection zone. This type of oscillation is one of many which are being studied to understand the internal structure of the sun. This area of research is called solar seismology. The stunning video captures an area of the sun roughly the size of our Earth, featuring granules roughly the size of a country, and resolves features as small as 30 kilometers across. Granule centers are bright due to the upwelling hot solar plasma, while the edges are dim due to the cooler plasma falling back. An interesting question related to the photosphere of the Sun is related to the sharpness of the solar limb. If Sun is actually a ball of plasma, that is charged gas, whose density decreases as we move further away from the center, then how is it possible that we see a very sharp boundary of the Sun, just like the boundary of the Earth's solid surface? Let me know your thoughts in the comments below before I answer that. The edges of the Sun look darker relative to the center. This phenomena, also seen among other stars and planets, is called limb darkening. Basically, this is a consequence of the fact that the intensity coming from near the edge of the Sun is lower and the line of sight passes farther from the center of the Sun. This causes the path length through the Sun to decrease and pass through less dense regions, making the solar disk appear darker towards the limb, that is the outer edge of the Sun. The amount of limb darkening allows astronomers to determine the temperature distribution in the Sun. It could also tell us a lot about the properties of the stellar atmosphere if we could see it, for example, during a solar eclipse. The chromosphere is the outermost layer of the Sun, but it allows most light to pass through it, so we only see the photosphere under normal conditions. The continuum radiation from the photosphere is so bright that the chromosphere is not even visible. However, during a total eclipse of the Sun, just before and after totality, that is, when the Sun's disk is fully covered, the Moon blocks the light from the photosphere but not from the chromosphere. For those brief instances, we see the red glow of the chromosphere. This red glow comes from the H-alpha line of hydrogen. Studying this line alone tells us a lot about the chromosphere. At the center of the H-alpha line, we can see down to about 1500 kilometers above the base of the photosphere. So by imaging the Sun at the wavelengths of the H-alpha line, astronomers study the structure of the chromosphere of the Sun. For instance, in this image taken in H-alpha, the granulation in the chromosphere of the Sun is seen on even larger scales. This is called supergranulation. The supergranules are 30,000 kilometers across. We also see small irregularities in the chromosphere. These are called spicules. These protrusions emerge from the Sun's surface 700 kilometers across and 7,000 kilometers high. The spectra of the chromosphere reveals that it is hotter than the photosphere, even though because it is so low in density, the chromosphere does not actually contribute enough to the radiation that we see coming from the Sun. It is an interesting problem to solve as to why does the temperature increases so far away from the center of the Sun. Beyond the chromosphere lies the Sun's corona. It is most apparent during a total solar eclipse when the much brighter light from the photosphere and chromosphere is blocked out. The corona is simply too faint to be seen in the presence of any photospheric light. As a result, it can only be studied during the rare total solar eclipse, which roughly occurs once every 1.5 years. In this sense, we are fortunate that the Moon subtends almost the same angle as the Sun as viewed from the Earth. The Moon can exactly block the photosphere and chromosphere, but not the corona. The corona can also be studied using radio waves. When we analyze the abundance of highly ionized elements, the broadening of their spectral lines, and the strength of the radio emission, the corona is found to be very hot at a temperature of around 2 million Kelvin. But at only a billionth of the density of the Earth's atmosphere, its density is very low. Various studies trying to explain the rise in temperature of the outer layers of the Sun relative to the chromosphere are still under scrutiny. In the photographs of the corona, its structure is also very irregular. Long streamers whose appearance varies with time are common features. Astronomers think that these phenomena are related to the Sun's magnetic field, just like many other aspects of the solar activity. Images of the Sun often show patterns of darker areas which are not as bright as the area surrounding it. The gas in the darker region is at a temperature of around 3800 Kelvin. A close-up of the sunspots show that they have a darker inner region called umbra, surrounded by a lighter region called the penumbra. The current understanding is that sunspots are regions where magnetic field is higher than the rest of the sun. The magnetic field of the sun is primarily attributed to moving charges. The number of sunspots on the sun are also not constant but vary in a regular pattern. It was realized in the mid-19th century that sunspot numbers follow an 11-year cycle. The number of sunspots in a peak year is not the same as another peak year, but the peaks are easily noticeable as can be seen in the image here. A more regular pattern appears when astronomers plot the height of each sunspot group above or below the sun's equator as a function of when they appeared in the sunspot cycle. This was first done in 1904 by E. Walter Maunder. He showed that the sunspots appeared farther from the sun's equator in the beginning of each 11-year cycle and closer to the equator later on. This results in a butterfly-like pattern in the plot, which is therefore called a butterfly diagram, as shown in the top panel here. The bottom panel of this figure shows the percentage of solar surface covered by the sunspots. When Maunder investigated records of the past sunspot activity, he found that there was an extended period of time from the year 1645 to 1715 when no sunspots were observed. This period is called the Maunder minimum to honor him. More recently, John Eddy found records which indicate that no aurorae were observed for many years during this period, and a very weak corona was observed during total solar eclipses which happened during that time. The growth rings of old trees also seem to show some correlation with this period of low solar activity, although the exact correlation is not yet fully understood. The magnetic field in sunspots are measured on the basis of the Zeeman effect, which is the shifting of energy levels in certain atoms when placed in a magnetic field. The magnetic field in the sun may be as large as 0.45 Tesla relative to the magnetic field of the Earth at the equator, which is just 0.03 millitesla. The strong magnetic field supports convection energy transport, which explains the lower temperature of the spots. Sunspots often occur in pairs where the components have opposite polarity, just like the two ends of a bar magnet. The structure of such bipolar groups, that is one sunspot corresponding to north while the other corresponding to the south pole, can be understood if the field rises into a loop above the solar surface, connecting the components of the pair. If gas is streaming along such a loop, it becomes visible as a loop prominence. As seen here, the prominences are among the most spectacular solar phenomena. They are glowing gas masses in the corona, easily observed near the edge of the sun. There are several types of prominences. The quiescent prominences, where the gas is slowly sinking along the magnetic field lines. Loop prominences, connected with magnetic field loops in sunspots. And the rarer, eruptive prominences, where gas is violently thrown outwards. The temperature of prominences is about 10,000 to 20,000 Kelvin. In H-alpha photographs of the chromosphere, the prominences appear as dark filaments against the solar surface. Besides sunspots and prominences, the sun shows several other types of surface activity: faculae and plages and flares. The faculae and plages are local bright regions in the photosphere and chromosphere respectively. Observations of the plages are made in the hydrogen H-alpha or the calcium K line. The plages usually occur where new sunspots are forming and disappear when the spots disappear. Apparently, they are caused by the enhanced heating of the chromosphere in strong magnetic fields. The flare outbursts are among the most violent form of solar activity. They appear as bright flashes lasting from 1 second to just under an hour. In the flares, a large amount of energy stored in the magnetic field is suddenly released. We are yet to fully understand the detailed mechanisms causing solar flares. Flares can be observed at all wavelengths. The X-ray emission of the sun may increase 100-fold during a flare. Several different types of flares are also observed at radio wavelengths, and the emission of solar cosmic ray particles also rise during flares. Prominences and flares are often accompanied with coronal mass ejections. These are fast-moving clouds which accelerate particles to very high velocities. Particles in a magnetic cloud traveling at the velocity of the mass ejection reaches the Earth in a couple of days. Particles activated by the shock wave arrive continuously, affecting the space weather and causing magnetic storms. They can even disrupt our satellites and destroy technology, and therefore are a crucial subject of study. Various solar observations, such as the Indian Aditya L1 mission and the European Space Agency's Solar Orbiter, provide wealth of data to understand our star. To conclude, the Sun is a complex sphere formed by many layers, each requiring unique strategy for exploring and providing an opportunity to investigate our life source, the Sun. I really hope you like this small astrophysical introduction to the Sun. If you learned something from this video, please check out the rest of our content and share it with other astronomy enthusiasts as well. I'll see you next week. Until then, take care.